In the depths of space, where the light from distant stars fades among endless voids, a journey continues, one that began more than 4 decades ago. It might have seemed that its path was confined to the boundaries of the solar system, but fate had other plans. What started as a scientific expedition gradually evolved into something greater, a chronicle of humanity's first touch with the interstellar abyss. Each year brings data that not only expands our understanding of space, but also raises far stranger questions. What secrets lie at the edges of the solar system? Why did what seemed like a normal explosion turn out to be the brightest ever observed? And how did 2 nearly identical probes experience such different fates on the same path? The answers lie ahead. Don't miss out. Subscribe and like if you feel the cosmos is only beginning to tell its true story. NASA's Voyager 1 and Voyager 2 spacecraft, launched in 1977 to study the outer planets of the solar system, have been operating for more than 45 years. They've exceeded their original missions and have become symbols of humanity's quest for knowledge. Onboard power is provided by radioisotope thermoelectric generators using plutonium-238, which lose about 4 watts of output each year. This compels scientists to gradually shut down instruments to extend the mission's life. NASA estimates the probes could cease operation by 2030, but there's hope they might continue until their 50th anniversary. Why did Voyager 1 detect a higher-than-expected plasma density, and what might this mean for our understanding of interstellar space? Does the increase in magnetic field strength beyond the heliopause, recorded by Voyager 2, point to unknown processes in the boundary region between our solar system and the galaxy? Could the rapid thickening of the interstellar medium detected by both Voyagers signal that they are nearing a completely new, unexplored region of space? The solar system has several boundaries, and one of them, the heliopause, is defined by the weakening of the solar wind. The space within this boundary is called the heliosphere, and beyond it begins the interstellar medium. The shape of the heliosphere is not spherical. It resembles an oval, with the solar system positioned closer to the front edge and trailing behind in a sort of tail. Though interstellar space is often thought of as a vacuum, that's not entirely accurate. The density of matter is extremely low, but it does exist. Within the solar system, solar wind density ranges from 3 to 10 particles per cubic centimeter and decreases with distance from the Sun. In comparison, the average electron concentration in the Milky Way's interstellar medium is estimated at 0.037 particles per cubic centimeter, while the plasma density in the outer heliosphere is around 0.002 electrons per cubic centimeter. When the Voyager probes reached the heliopause, their instruments recorded plasma electron density through analysis of plasma oscillations. Voyager 1 crossed the heliopause in 2012 at a distance of 121.6 astronomical units from Earth. In October 2013, it recorded plasma oscillations that revealed a plasma density of 0.055 electrons per cubic centimeter. After traveling another 20 astronomical units, equivalent to 2.9 billion kilometers, the probe reported an increase in interstellar plasma density to 0.13 electrons per cubic centimeter. Voyager 2 crossed the heliopause in 2018 at a distance of 119 astronomical units. Its measurements showed a plasma density of 0.039 electrons per cubic centimeter. In 2019, at a distance of 124.2 astronomical units, or 18.5 billion kilometers, it recorded a sharp increase in density to about 0.12 electrons per cubic centimeter. One hypothesis explaining this increase suggests that the interstellar magnetic field strengthens beyond the heliopause, potentially causing electromagnetic ion cyclotron instability. Supporting this idea, Voyager 2 recorded increased magnetic field strength beyond the heliosphere. Another theory suggests the interstellar wind slows near the heliopause, leading to a buildup of matter in a plug-like region. Why was it Voyager 1, already beyond the heliosphere, that first detected signals from one of the most powerful gamma-ray bursts in history? What data recorded by the probe could transform our understanding of high-energy cosmic phenomena? Could Voyager 1 become a key witness to other cataclysmic events beyond the solar system? On October 9, 2022, the solar system was struck by the most powerful gamma-ray burst ever recorded. NASA confirmed that this unprecedentedly bright event was detected by multiple instruments, including the Voyager 1 interplanetary spacecraft. It was the first to detect a sharp spike in high-energy particles preceding the burst, which later proved to be 70 times brighter than any similar event known to astronomers. Gamma-ray bursts remain one of the most mysterious subjects in modern astrophysics. They were first discovered in 1967 thanks to the Vela satellites, launched in 1963 to monitor possible nuclear explosions on Earth. Since then, science has closely studied these high-energy events, as they may be linked to the early stages of the universe. The burst detected in 2022 was designated GRB22109A. Researchers estimate its signal traveled nearly 2 billion years through space before reaching Earth. NASA noted that such an event is extremely rare, perhaps occurring no more than once every 10,000 years. It is believed that this massive energy release was caused by the formation of a black hole. Scientists associate the further study of GRB22109A with the potential to gain new insights into the structure of interstellar dust clouds and the mechanisms underlying the formation and evolution of black holes. The deeper we venture into the interstellar darkness, the clearer it becomes. The Voyagers are no longer just probes. They have become messengers of humanity in a space where there is neither light nor sound, only silence filled with questions. Perhaps these spacecraft will be the first to send us evidence of phenomena we are not yet prepared to face. What if, beyond the edge of the known, there is not emptiness, but a door? What if the sudden density spikes, magnetic storms, and bursts of energy are not just noise, but someone's trace? And while science is still searching for the keys to these mysteries, the spacecraft silently continue onward, into a realm where the boundaries of space and time lose their meaning. Subscribe to the channel and stay tuned, because the most fascinating part may only just be beginning.